Hi, I'm Alan. I'm a junior majoring in physics and minoring math. And today I want to introduce you to quantum mechanics by specifically talking about the operator. So, if you can still recall from your high school physics, or if you already taken physics 1, you were learning about Newton's law of motion, which specifically Newton's second law, which describes how the force acts on an object with some mass. So, here you have the force and you also have the mass, which is constant, and you also have the acceleration, which is the second derivative of the position. If you're not sure what the second derivative of the position means for now, don't stress about it. And you can also write it this way, which is a fancy way to write the second derivative of the position. And this is the expanded version. And quantum mechanics, which when objects are getting too small, we can't really describe them with Newton's law of motion. Quantum mechanics is basically based on two constructs, which first you have the state of the system. We describe them with wave functions. And there's also observables, which we represent them as operators. So examples of state of the system could be an atom. This is a picture of a real hydrogen atom. Could be some molecule. And for observables, they could be their position or their momentum and could be their energy. So how does operators act on the state of the system? It's like they act on the state of the system and it gives you a new state of system which the operator multiplies on the state of the system and gives you back some value times the state of the system. So these wave functions are actually defined by vectors, and the operators are acts on them like linear transformations. If you haven't get into the vectors and linear algebra in general, don't stress about it as well. So a transformation in this case, which is the operator, is the value we're trying to measure. Say we're trying to measure the position of the molecule, are represented by matrices. And the operator acts on a vector, which basically multiply on them by matrix multiplication. So we have the state of system. These are just the components of them with indexes. And here you have the transformation times the state of the system, which the operator itself is this big matrix here. And you also have the original state of the system. So there are many types of quantum operators. So here, this one, this H, we call it the Hamiltonian. It gives you the energy of the system. Here we also have the X operator, which gives you the position of the system, which is just X times the system itself. Here also the momentum, which is the mass times the velocity. This one here is actually simplified, but you don't need to worry about it for now. And here's velocity is quoted because in quantum mechanics, these velocities are much more complicated to describe. So in general, operators acts on the state of system, gives you the eigenvalues times the state of system. The eigenvalue is just a fancy way to say the measurement you're trying to get. At last, I introduce you to Schrodinger's equation, which is Newton's second law equivalent in quantum mechanics. It's exactly the same form for the time-independent one as the Hamiltonian axon and wave function that gives you the energy of the wave function, which is the system you're trying to describe. So compared to Newton's second law, imagine this acceleration here, analogous to an operator, acts on the mass, and it gives you the force of the system you're trying to describe. Thank you.